6 billion light years from where you breathe tonight, something is bending the fabric of reality itself. Not a galaxy, not a cluster. Something so massive that light itself cannot travel straight in its presence. Something so ancient it was already old, when our sun was nothing but scattered dust drifting through an empty void. James Webb, the most powerful eye humanity has ever opened toward the cosmos, locked onto this region during a routine scan. What it found made an entire research team fall silent. A gravitational signature so far outside expected values that the scientist who first noticed it read the number 3 times before trusting their own eyes. A structure so vast that if you began crossing it at the speed of light, you would die of old age before completing even a fraction of the journey. Your children would continue, their children after them. Generations upon generations of travelers, none ever arriving. And at the center of this impossible architecture, wrapped in the deepest cold between galaxies, Webb detected something that should not exist. A warmth. Faint. Persistent. Steady across billions of years. Something is inside this structure. Something generating energy in a region where physics says nothing should survive. Something that has been waiting there since before the first stars ignited. If explorations like this speak to the part of you that stares up at the night sky and wonders what else is out there, consider subscribing and leaving a like. It helps more than you know. Now take a breath. Let the journey begin. There is a kind of silence that only happens when someone sees a number they cannot believe. Not the silence of an empty room. Not the silence of boredom or distraction. This is the silence of a mind hitting a wall. The kind where your hands stop moving, your breath catches somewhere behind your ribs, and you read the same line again, because the first reading could not possibly be right. That is exactly what happened roughly 6 billion light years from where you are sitting right now. Not at the location itself, of course, but inside a quiet office, where a researcher was doing something deeply ordinary. They were sorting data, running a routine deep field scan with the James Webb Space Telescope, cataloguing galaxies in a region of space that was supposed to be well understood, the kind of work that fills databases, not front pages, the kind of afternoon where you expect nothing and find even less. But buried inside that stream of numbers was a gravitational reading that did not belong, a measurement of how much mass was sitting in one particular patch of sky. And that measurement was wrong. Not slightly wrong. Not the kind of wrong you fix by adjusting a decimal point or rechecking your units. It was the kind of wrong that makes you put down your coffee, lean closer to the screen, and read the number a third time with your heart beating just a little faster than before. The reading came from a gravitational effect called lensing. Picture a magnifying glass, but instead of glass bending light, it is mass. When something enormously heavy sits in space, it bends the fabric of space itself. Light traveling near that mass follows the curve. It warps. It stretches. Background objects behind the mass appear distorted, smeared into arcs and strange shapes when viewed from far away. The heavier the object, the stronger the bending. Scientists use this bending like a scale. They measure how much the light curves, and from that curve, they calculate how much mass must be there to cause it. In this patch of sky, the bending was far too strong. The galaxies visible in that region could not account for it. Not even close. It was like stepping onto a bathroom scale and watching it read 5,000 pounds. You know something is wrong. You just do not know what yet. Now here is the thing about science that most people never see. There is no dramatic music in the background. There is no team of people gasping at once. What actually happens is quieter and in some ways more powerful. The astronomer who noticed the number did not shout. They did not call a press conference. They opened their email, wrote a short message to a colleague, and said something close to this: "Can you look at this and tell me I am wrong?" That email is where the story really begins. Because the colleague looked, and they could not tell them they were wrong. A second researcher joined, then a third, then a fourth. Within weeks, a small informal group had formed around this one strange number, each of them approaching it from a slightly different angle. One checked whether the telescope itself had made an error. Webb, like any instrument pushed to the edge of what human engineering can build, is not perfectly immune to false signals. Small glitches in the detector can create phantom readings, ghost numbers that look real but come from the machine rather than the universe. The team ran calibration checks. They compared the signal across different parts of the detector. They isolated the reading and tested it against every known pattern of instrument noise. The signal was real. A second observation was scheduled. Webb turned back to that same patch of sky and gathered more light, more data, more time. The reading came back stronger, cleaner. The mass hiding in that region was not a mistake. It was not a ghost. It was there, pulling at everything around it with a gravity that our maps said should not exist in that location. And this is where the number became something more than a number. Because what the team realized, slowly and carefully over the weeks that followed, was that the mass was not spread out randomly like a fog. It was organized. It was concentrated toward a center. It had edges. It had shape. The gravitational field they were measuring was not the signature of a scattered cloud of invisible material drifting through space. It was the signature of a structure, something with architecture, something with a form you could almost draw if you had a pencil large enough to sketch across millions of light years. The word structure was used carefully in those early internal reports. Scientists are trained to be cautious with language. Calling something a structure means you are saying it has boundaries. It has an inside and an outside. It has a center and a perimeter. That is a commitment. That is saying this thing is real and it is organized, and it demands an explanation. Here is a fact that will help you feel the weight of what they were facing. Dark matter, the invisible substance that makes up roughly 85% of all matter in the universe, was already factored into their calculations. They knew it was there. They expected it to add invisible weight to the region. Every standard model of mass distribution includes dark matter as a silent partner, adding gravity without ever showing itself to a telescope. Even with dark matter included, the numbers did not work. The mass excess, as scientists call it, was still far too large. Something was sitting in that region of space that went beyond what visible galaxies and invisible dark matter together could explain. There is a small and fascinating detail worth pausing on. In the history of astronomy, some of the most important discoveries started exactly like this. As footnotes, as anomalies buried in routine data that someone almost scrolled past. The planet Neptune was found because Uranus was not quite where it should have been. A tiny wobble, a small wrong number, led to the discovery of an entire world. Dark matter itself was first suspected because galaxies were spinning faster than their visible mass should allow. A wrong number again. The universe has a habit of hiding its biggest secrets inside its smallest errors, and this error, this mass excess 6 billion light years away, carried a detail that would eventually draw the attention of the entire astronomical community. Because the concentration of mass at the center of this structure was not just large, it was generating a faint signal of its own, a whisper of infrared warmth coming from deep inside, where nothing warm should be. That detail sat quietly in the footnotes of the first internal report, almost overlooked, almost ignored. But as we will soon discover, that warmth would become the single most important and most troubling piece of this entire puzzle. Because empty space does not glow. Cold, dark matter does not radiate heat, and something buried at the heart of a structure that should not exist was doing both. The emails kept circulating, the team kept growing, and the universe, as it always does, kept waiting for someone to ask the right question. We use the word massive every day. A massive storm, a massive crowd, a massive burger at the restaurant down the street. We have used it so many times that it has gone soft in our mouths. It has lost its teeth. It means big now, nothing more, just big, and we move on without feeling anything at all. So before we go any further into what James Webb found out there in the deep, let us stop and rebuild that word from the ground up. Let us put real weight back into it, because what we are about to describe will need every ounce of meaning that word was ever meant to carry. Start with where you are, the ground beneath you, the sky above you, the planet you are resting on right now. Earth is large enough that no human being has ever seen all of it. You could spend your entire life walking and still leave most of its surface untouched. It is 8,000 miles across, a sphere of rock and iron and water spinning through the dark. That feels big, and it is, compared to you. Now pull back. Earth orbits a star. Our sun, the sun is so large that you could fit more than 1 million Earths inside it and still have room. If Earth were a marble, the sun would be a door. The distance between them is about 93 million miles. Light, the fastest thing in the universe, takes 8 minutes to cross that gap. 8 minutes. That is how far away the nearest star is to us, and it is practically sitting in our lap compared to what comes next. Our sun is one star among hundreds of billions inside the Milky Way galaxy. Somewhere between 100 billion and 400 billion stars live in this galaxy, depending on which estimate you trust. The Milky Way stretches roughly 100,000 light-years from one side to the other. A single light-year is about 6 trillion miles, so 100,000 of those, lined up end to end, and you start to feel the floor tilting under your sense of scale. The Milky Way is enormous by any measure a human mind can hold. It contains more stars than there are grains of sand on many of the beaches you have ever visited. And yet, the Milky Way is not alone. Our galaxy belongs to a small family called the Local Group. About 50 galaxies clustered together by gravity, stretching across roughly 10 million light-years of space. The Milky Way and Andromeda are the two biggest members. The rest are smaller, dimmer, orbiting quietly like moons around two great campfires. 10 million light-years across. That sounds like it must be close to the ceiling. The biggest thing there is. It is not even close. The Local Group sits inside a much larger structure called the Virgo supercluster. Thousands of galaxies spread across more than 100 million light-years, and even the Virgo supercluster is just one small neighborhood inside something far greater. A structure called Laniakea. The name comes from Hawaiian. It means immeasurable heaven, and it earns that name. Laniakea stretches roughly 500 million light-years across and contains the mass of 100 million billion stars. When you hear that number, your brain does something interesting. It stops trying to picture it. It files the number away as simply very large and moves on. That is a survival mechanism. Your mind protects itself from scales it was never built to hold. Most people hearing about Lanaya assume we have finally hit the top, that nothing could be bigger, that the ladder of scale ends here. It does not. There are structures in the universe that make Laniatea look like a single thread in an enormous carpet. The Hercules Corona Borealis Great Wall, confirmed by gamma-ray observations, stretches roughly 10 billion light-years across. It is the largest known structure in the observable universe, a wall of galaxies and gas and dark matter so vast that its existence alone troubles scientists, because according to a principle called the cosmological principle, the universe at very large scales should look roughly the same in every direction. Matter should be spread more or less evenly, not clumped into walls and filaments and sheets that stretch across significant portions of the entire observable cosmos. When something gets big enough, it starts to argue with the rules, and the structure that Webb found may be sitting right at that argument or past it entirely. Now hold that entire ladder in your mind. Earth, the Sun, the Milky Way, the local group, the Virgo supercluster, Laniakea, the Great Wall. Hold all of it, stacked up, each step making the one before it looks small and almost silly. And now understand this: the structure Webb detected operates at a scale that rivals or potentially exceeds the largest things we have ever confirmed. If you tried to cross it traveling at the speed of light, the journey would take longer than the entire history of human civilization, multiple times over. You would be born, live your full life, and die. And the crossing would not be close to finished. Your children would face the same fate, and their children after them. Generations stacked upon generations, all of them travelers, none of them ever arriving. That is what massive means here. Not big, not impressive, not worth a second glance. It means something that breaks the part of your mind designed to understand distance and laughs at the pieces. But here is what separates this discovery from being just another entry in the record book of large things. Size alone, as astonishing as it is, would simply be a curiosity. Scientists would catalogue it, note it as unusual, and move forward. What makes this structure different is that its size comes paired with something far more unsettling. Organization. This is not a random smear of mass scattered across space like paint thrown at a wall. It has edges, it has a defined center, and it has a concentration of mass at its core that behaves unlike anything in any catalogue ever assembled. There is a speculative idea that lives at the edges of cosmology, one that most researchers mention only quietly, almost as a thought experiment. What if the cosmological principle, the assumption that the universe looks the same everywhere at large scales, is not a law of nature, but merely an approximation? What if the universe at its largest scales is fundamentally lumpy, fundamentally uneven, built with a grain and texture that our current models have smoothed away for simplicity? Structures like the one Webb found push that question from the edge of conversation toward the center. The debate remains open and unsettled. Some cosmologists argue that these enormous structures are statistical outliers, rare but permitted by existing models if you account for the full range of possible density variations in the early universe. Others argue that the growing catalogue of impossibly large structures, Webb adding new entries with almost every deep observation, points towards something missing in our framework. Something fundamental about how matter organizes itself at the grandest scales that we have not yet understood. We have climbed the ladder now. From a marble-sized Earth to a structure that swallows galaxies the way rivers swallow raindrops. But knowing how large something is only tells you part of the story. To understand how Webb found it, how it peeled back the darkness and the dust and the billions of years of distance to see something that had been hiding since long before our planet was born, you need to understand the instrument itself, the golden eye that does not see the universe as it is, but as it was. Every telescope is blind to something. That is not a flaw. That is simply how light works. The universe does not communicate in one language. It speaks in dozens, hundreds, each one a different wavelength of light. Radio waves carry one kind of story. X-rays carry another. Visible light, the narrow band your eyes happen to be tuned to, carries only a tiny fraction of the full conversation. When you look up at the night sky with your bare eyes, you are hearing a whisper and mistaking it for the whole song. James Webb was built to hear a part of the song that had been almost entirely silent to us before. Infrared light. You cannot see infrared, but you have felt it your entire life. It is the warmth on your skin when you stand near a fire. It is the heat rising off a summer road. In space, infrared carries something far more precious than warmth. It carries information from places that visible light can never reach. Here is why that matters. Between us and any object 6 billion light years away, space is not empty. It is filled with obstacles. Clouds of gas stretching across thousands of light years, veils of dust scattered by ancient exploded stars, thin halos of diffuse material surrounding galaxies, too faint to photograph but thick enough to block and scatter ordinary starlight. For decades, anything hiding behind this cosmic haze was invisible to us. We suspected things were there because of indirect clues, a gravitational tug here, a missing piece of the puzzle there. But we could not see them. Infrared light passes through these obstacles the way sunlight passes through morning fog. It slips past the dust and gas that stop visible light cold. Webb was designed to catch that infrared glow after it traveled billions of years across the universe, weakened and stretched by the expansion of space, but still carrying the fingerprints of whatever produced it. The machine itself is a piece of engineering that borders on the unbelievable. At its heart sits a primary mirror nearly 2 stories tall, assembled from 18 hexagonal segments fitted together like a honeycomb. Each segment is coated in a thin layer of gold, not for decoration. Gold reflects infrared light better than almost any other material. When an infrared photon that has been traveling since before Earth existed finally reaches Webb, it strikes that golden surface and bounces inward toward the detectors, where it is caught and read like a letter from the ancient universe. The mirror's total surface area is roughly 6 times larger than the mirror on the Hubble Space Telescope. In astronomy, surface area is everything. A bigger mirror collects more light. More light means you can see fainter objects, older objects, objects so distant and so dim that they are barely more than a suggestion against the black. Webb does not just see further than Hubble, it sees into a completely different era of cosmic history, an era Hubble could only squint at and guess about. But the mirror alone is not enough. To detect the faintest infrared signals from the deepest reaches of space, Webb needs to be cold. Desperately, impossibly cold. Any warmth near the detectors would drown out the signals it is trying to catch, the way a flashlight drowns out a candle. So Webb does not orbit Earth the way Hubble does. It sits at a point in space called Lagrange Point 2, roughly 1 million miles from our planet, on the side facing away from the Sun. There, a sun shield the size of a tennis court blocks the light and heat of our star, keeping Webb's instruments in permanent shadow. The temperature on the cold side of that shield drops to around minus 370 degrees Fahrenheit. At that temperature, Webb's detectors become sensitive enough to measure temperature differences smaller than a fraction of a single degree. That is the level of precision that made this discovery possible. Now here is something that changes how you think about everything Webb shows us. Because light travels at a fixed speed, looking deep into space is always looking backward in time. The light from the sun takes 8 minutes to reach your eyes, so when you glance at the sun, you see it as it was 8 minutes ago. The light from the nearest star beyond the sun takes over 4 years. The light from distant galaxies takes billions of years. When Webb observed this structure 6 billion light years away, it was not seeing what exists there today. It was seeing what existed there 6 billion years ago. The universe was roughly half its current age. The cosmic web of galaxies and filaments was already well established. Most of the stars that would ever be born were already burning or forming. It was a middle-aged cosmos, settling into patterns that would define its appearance for billions of years to come. And yet, in that middle-aged, supposedly well-understood epoch, Webb saw something that our models say should not have been there. Light from galaxies far behind the structure was bending, subtly, consistently, unmistakably, bending around something enormous that was warping the fabric of space the way a bowling ball warps a rubber sheet. The degree of bending told Webb's scientists exactly how much mass was causing it, and that mass was far too great to be explained by anything visible in the region. There is an odd detail about Webb that most people never consider. The telescope does not send its data to Earth in real time. The information travels as radio signals across that million-mile gap, arriving at ground stations where it is processed through a complex pipeline of calibration software before any human eye ever sees a single image or number. The raw data that comes off Webb's detectors looks nothing like the stunning photographs released to the public. It is a stream of numbers, pixel values, wavelength measurements, noise patterns. The beauty you see in Webb's images is extracted from that raw stream by teams of scientists who spend weeks cleaning, calibrating, and interpreting it. This process matters because it means every discovery Webb makes passes through multiple layers of human verification before it is trusted. The gravitational anomaly in this structure was not a single dramatic image that someone gasped at. It was a pattern hidden inside thousands of data points, visible only after careful analysis and comparison across multiple observation windows. The signal emerged slowly, like a shape forming in fog, growing clearer with each pass until the team could no longer explain it away. There is a speculative thought that some astronomers have raised quietly about Webb's placement at Lagrange Point 2. Because it sits so far from Earth, permanently facing away from the Sun, it occupies one of the loneliest positions any human-made object has ever held. If something were to go wrong with the telescope, no repair mission could reach it. Unlike Hubble, which astronauts visited and fixed multiple times, Webb is beyond rescue. Every observation it makes carries a quiet weight of finality. The data it gathers may be the only chance we get to see certain objects with this level of clarity for decades to come. That weight makes what it found 6 billion light-years away feel even more urgent. Because the signal Webb pulled from that ancient light was not just unusual, it was the kind of signal that demanded confirmation, demanded repetition, demanded months of careful, painstaking work before anyone dared to call it real. And that slow, stubborn process of turning a strange number into an undeniable truth is exactly where our journey takes us next. A signal means nothing until it survives every attempt to kill it. That is not poetry. That is how science works. You find something strange, and then you spend weeks, months, sometimes years trying to prove it is not real. You test it against instrument errors. You test it against known noise patterns. You hand it to someone who has never seen it before, and ask them to tear it apart. Only when the signal refuses to die When it stands up after every blow and looks back at you unchanged, do you begin to trust it? The gravitational lensing anomaly Webb detected in that patch of sky 6 billion light-years away had to survive exactly this kind of trial. And it did. Not once, not twice, but through a process so thorough and so cautious that by the time the team was ready to say the word real out loud, roughly 18 months had passed since the first strange number appeared on a screen. Let us walk through what that process looked like, because it tells you something important about the difference between finding something and knowing something. Finding is the easy part. It is the moment the number appears. Knowing takes everything you have. The first thing the team did was check the instrument. Webb is the most advanced telescope ever built, but it is still a machine. Machines create artifacts, small false signals that come from the detector itself rather than from the universe. A cosmic ray striking a sensor at the wrong moment can leave a mark that looks like a real signal. A tiny vibration in the spacecraft can shift a reading just enough to create a phantom. Thermal fluctuations in the detectors, even at Webb's extreme cold, can introduce noise that mimics genuine data. The team ran calibration checks across every detector segment involved in the observation. They compared the anomalous reading against the known behavior of the instrument in similar conditions. They looked for any pattern that would suggest the signal was coming from inside the telescope rather than from outside it. The signal passed every test. It was not an artifact. It was not a glitch. It was coming from space. The second step was repetition. A single observation, no matter how clean, is never enough. Science does not trust single measurements. Too many things can go wrong once, but if you point the telescope at the same patch of sky a second time, weeks or months later, with different detector conditions and different calibration settings, and the signal comes back exactly the same, the odds of it being a fluke drop dramatically. Webb turned back to that region of sky and gathered more light, more data, more time. The lensing pattern returned, stronger now, because the second observation was longer and captured more photons from the background galaxies whose light was being bent. The mass excess was confirmed. Whatever was sitting in that region was still there, still pulling, still bending space around it with a gravity that the visible contents of that sky could not explain. The third step was the one that separates careful science from ordinary curiosity. The team passed the data to independent groups, not colleagues who had been following the work, not friends who might be sympathetic, separate teams at separate institutions who had no stake in the outcome and no reason to see what they wanted to see. Each independent group received the raw data and ran their own analysis using their own methods. Each time, the result came back the same. The mass excess was real, the gravitational lensing was genuine, and the concentration of that mass toward a center point was not a processing artifact. It was a feature of the universe. Now here is where the story deepens. Because during the second observation run, something new appeared in the data, something the first pass had only hinted at. The mass was not just concentrated, it was concentrated in a way that had a specific pattern. The gravitational signal peaked sharply toward a central location, rather than spreading out gradually the way a diffuse cloud of dark matter would. This is an important difference. Imagine pouring honey onto a plate. It spreads outward, thinning as it goes, forming a smooth, gentle slope from the center to the edge. Now imagine placing a heavy marble at the center of that honey. The marble creates a sharp dip, a sudden concentration that is fundamentally different from the gentle spread around it. The gravitational map of this structure looked like the plate of honey, with a marble sitting in the middle. Something was anchoring the center, something denser and more compact than the surrounding mass. This is the moment where the team had to make a decision about language. In science, words carry weight. You do not call something a structure unless you are prepared to defend that word. A structure implies organization. It implies boundaries. It implies something that has an inside and an outside, a center and an edge. Calling this anomaly a structure meant committing to the idea that what Webb found was not just a random excess of mass floating through deep space. It was something shaped, something held together, something with architecture. The word appeared in the internal reports first, carefully, surrounded by qualifiers and hedges. Possible structure, apparent structure, candidate structure. But with each round of verification, the qualifiers began to fall away. The data kept pointing in the same direction. This was real. This had form. And this had something sitting at its center that was generating not just gravity, but a faint, consistent warmth that should not have been there. There is a strange and little-known detail about how scientific discoveries travel through the community before they reach the public. The first draft of the paper describing this anomaly was circulated privately among a small group of reviewers. Their job was to find mistakes, to challenge every assumption, to ask the hardest possible questions. Several prominent voices pushed back. The mass excess could still be explained by exotic dark matter behavior, they argued. The edges of the structure might be a processing artifact rather than a real boundary. The central signal might be a coincidence, two unrelated objects lining up along the same sightline. These were fair challenges, good ones, the kind of questions that make science stronger rather than weaker. But each time a critic proposed a simpler explanation and tested it against the data, something did not fit. The ordinary explanations kept falling short. They could explain part of the picture, but never all of it at once. The lensing was too strong. The concentration was too sharp. The warmth was too consistent. And all three were present at the same location, pointing at the same center, telling the same story. When the paper was formally published, the response moved through the astronomical community the way ripples move through still water. First, a small circle of specialists, then broader groups of cosmologists, then the wider scientific world. The skepticism did not disappear, it simply shifted. The question was no longer whether the anomaly existed. That debate was settled. The question became what exactly it was, and that question, as the months that followed would reveal, was far harder than anyone expected, because describing the shape of what Webb found requires a kind of imagination that textbooks do not teach, the kind that asks you to picture something that has never been seen before, built from clues written in bent light and ancient gravity. The shape itself is where we go next. There is no photograph of this structure. That needs to be said clearly because the human mind wants a picture. We are visual creatures. We want to see the thing, hold its shape in our imagination, point at its edges and say there, that is where it begins, and there is where it ends. But what Webb captured is not a snapshot of an object floating in space the way a planet or a galaxy appears in a telescope image. What we have instead is a gravitational map, a portrait drawn not with light, but with the bending of space itself. And that portrait, once assembled from months of careful data, reveals something genuinely strange. The structure is not round. This matters more than it might seem at first. Most large accumulations of mass in the universe tend toward roundness over time. Gravity is patient. It pulls inward from every direction equally. Given enough billions of years, it smooths things out, rounds off the corners, shapes matter into spheres and near spheres the way a river smooths stones. Galaxies are roughly disc-shaped or elliptical. Galaxy clusters are roughly spherical. The largest dark matter halos predicted by our models settle into round or slightly flattened shapes over cosmic time. This structure did not follow that script. Its gravitational footprint is elongated, stretched along one direction, compressed along another. The shape, described in rough terms, resembles a flattened spindle, wide across its middle, tapering toward two ends like a lens seen from the side, or an eye, half closed, stretched across a region of space so vast that the Milky Way would vanish inside it the way a single cell vanishes inside a human body. Shape carries information about history. When you look at a river stone, smooth and round, you know without being told that water shaped it over time. When you look at a jagged rock freshly broken from a cliff, you know something sudden happened. The elongated shape of this structure is telling us something about how it was made. A simple inward collapse of matter under gravity would not produce this geometry. Something guided its form. Either the original material it grew from had a specific shape to begin with, stretched along one direction by conditions in the early universe, or some external force acted on it over time, compressing it from outside along one axis while it expanded along another. Neither of those explanations is ordinary. Both require conditions that go beyond the standard story of how large-scale structures form. The overall reach of the structure, measured by how far its gravitational influence extends, covers an enormous region. But the most interesting part is not the edges. It is the center. The gravitational signal does not spread evenly across the structure like butter across bread. It peaks, sharply, toward a roughly central zone where the lensing is strongest, where the mass is densest, and where whatever is generating the anomalous readings appears to be concentrated. Picture a fog bank settling over a coastline. Most of the fog is thin and wide. You can see through it. You can feel that it is barely there. But at the heart of the bank, the fog thickens. Visibility drops to almost nothing. The air feels heavier. The density at the center is dramatically greater than at the edges. The structure behaves the same way. Its outer regions are broad and diffuse. Its core is something else entirely. Tight, heavy, anchored, and around the edges of this enormous shape, Webb found something that added another layer to the puzzle. Galaxies, not young, bright, active galaxies full of new stars being born. Old ones. Ancient ones. Among the earliest galaxy populations Webb has catalogued in that region of sky. Their light tells the story of their age. Young stars burn hot and blue. Old stars burn cool and red. The spectra of these galaxies are dominated by old, red, fading stellar populations. Their star-forming days ended long ago. But here is the detail that stopped researchers in their tracks. These ancient galaxies are not scattered randomly around the structure. They follow its shape. They cluster along its elongated axis, lining up with the spindle like beads threaded onto a wire, or like crystals forming along a crack in a piece of rock, guided into position by forces that were already in place when they first began to grow. Scientists call this a preferred orientation. It means the galaxies did not end up in these positions by accident. They were drawn there, guided by the gravitational field of the structure itself, and the pattern of their positions suggests something deeply unusual about the timeline of events. In standard cosmological models, structures form because galaxies already exist and their mutual gravity draws them together over time. Small things come first. Big things come later, built from the small pieces. Galaxies form, then galaxy groups, then clusters, then superclusters. The hierarchy goes from bottom to top, small to large, young to old. This structure appears to have reversed that order. The galaxies did not come first and then build the structure. The structure came first, and the galaxies organized themselves around it. They formed in its gravitational shadow. They grew along its spine. They were shaped by its presence while they were still young and still forming their first generations of stars. That sequencing changes everything. Because if the structure was already in place when these ancient galaxies were being born, then it did not form from galaxy-scale material. It formed from something older, something that existed before the first stars ignited, something that was already sitting there, massive and organized, when the universe was still in its infancy. There is a speculative idea that hovers around discoveries like this one, rarely spoken in formal papers, but alive in the hallways of conferences and the quiet conversations between researchers after the talks are finished. What if some of the largest structures in the universe are not built from the bottom up at all? What if certain extreme conditions in the very early universe allowed structures to form from the top down, collapsing directly from enormous primordial density variations without waiting for galaxies to assemble first? This idea challenges the hierarchical model that has served cosmology well for decades. It does not destroy it, but it suggests the hierarchy may have exceptions, and those exceptions may be sitting in the deepest, oldest corners of the cosmos, waiting for an instrument sharp enough to find them. Webb found one. And what makes it more than just a shape on a gravitational map is what is happening at its center. Because the edges tell you what the structure looks like. The ancient galaxies tell you when it formed, but the core, that dense, warm, impossibly concentrated center, tells you what it is. Or rather, it tells you what it might be. Because nothing in any catalogue quite matches what Webb measured coming from inside that core. A warmth that should not exist, a mass that should not be there, a signal that the deepest cold of intergalactic space cannot explain. And understanding that warmth requires understanding something simple but profound about the nature of empty space itself. Empty things do not pull. That sounds so simple it barely needs saying. But it is one of the most important rules the universe follows, and it is the rule that makes what Webb found at the center of this structure so deeply troubling. Gravity requires mass. A region of space with nothing in it has no gravitational voice. It does not tug at passing light. It does not draw nearby galaxies toward it. It does not bend the fabric of space into curves and wells. It simply sits there, invisible and inert, and the universe flows around it without noticing. The core of this structure is not empty. We know this not because we can see what is inside it, but because of what the inside does to everything around it. The gravitational lensing pattern across the structure is not uniform. If the mass were spread evenly from edge to edge, the bending of background light would be consistent, gentle, the same strength everywhere you measured it. Instead, the bending is strongest at the center, dramatically strongest. The kind of steep gravitational gradient you would expect if something heavy and compact was sitting specifically at the core, pulling space inward around itself like water swirling toward a drain. Something is in there, and Webb went looking for it. The first approach was radiation. Whenever matter does something energetic in the universe, it tends to announce itself. Gas falling toward a gravitational center heats up and glows. Colliding particles release X-rays. Spinning magnetic fields produce radio waves. Hot dust radiates infrared. If something massive and active was sitting at the core, it should be emitting radiation of some kind. Webb pointed its infrared detectors at the center and searched for any emission that could identify the source. What it found was quiet, almost too quiet, a faint infrared excess. That means slightly more infrared radiation coming from the core region than the surrounding empty space would naturally produce. Not a blazing beacon, not a bright source lighting up the interior like a lantern in a dark room. Something softer, a warmth, gentle, persistent and consistent across multiple observation windows. The core was not flaring or pulsing. It was simply warm, steadily, quietly, as though it had been warm for a very long time and intended to stay that way. Now, space is cold, not just chilly. The background temperature of the universe, the leftover warmth from the Big Bang itself, has cooled over nearly 14 billion years to just a few degrees above absolute zero. In the voids between galaxy clusters, in the dark stretches between the threads of the cosmic web, temperatures hover near that basement floor. Almost nothing. Almost as cold can get. For something to be measurably warmer than that baseline in a region of deep space means energy is being deposited there. Something is producing heat. And here is the part that makes this so difficult. Heat does not last. The universe is extraordinarily efficient at draining warmth away into the surrounding void. Energy spreads outward. Hot things cool down. If something was warm a billion years ago and nothing has been feeding that warmth since, it should be cold by now. Long cold. Stone cold. The kind of cold that matches everything else in the abyss around it. The core of this structure is not cold, it is warm right now. Or rather, it was warm 6 billion years ago when the light Webb captured left that region. And that persistent warmth implies something remarkable, not a one-time event. Not an ancient explosion that left a fading glow. An ongoing process. Something that was actively generating heat at the midpoint of the universe's life. Something that had likely been doing so for billions of years already by that point. The team considered every straightforward explanation they could construct. A dense cluster of ancient dim galaxies could in theory produce a combined infrared glow without any single source being bright enough to identify individually. Webb searched the core for individual galaxy signatures. It found a few, but not nearly enough. The galaxies present were too few and too faint to account for the total infrared output. The warmth was greater than what those dim residents could produce. A second possibility was hot gas, diffuse plasma heated by gravitational processes long ago, sitting at the center in a thin spread-out cloud, slowly radiating its stored energy. Hot gas does radiate. But gas at the temperatures needed to explain this infrared signal would also emit strongly in X-rays, and the X-ray data from that region, gathered by other observatories, does not support a massive cloud of superheated gas at the core. The X-ray signature is too weak. The gas explanation falls short. A third candidate was dark matter itself. Dark matter makes up roughly 85% of all mass in the universe. It provides the gravitational scaffolding that holds galaxies together and gives the cosmic web its shape. Without it, nothing you see in the night sky would exist as it does. Dark matter is real, and it is everywhere. But dark matter has a limitation that matters enormously here. It does not interact with light. It cannot absorb photons. It cannot emit them. It cannot scatter them. It is, to every detector humanity has ever built, completely invisible except for the gravity it produces. The infrared warmth at the core requires something that produces or interacts with photons. Dark matter cannot do this. So dark matter is almost certainly part of the structure. A large part, the broad gravitational architecture, the overall mass distribution across the elongated body almost certainly reflects an enormous dark matter concentration shaped by billions of years of gravitational dynamics. But dark matter is not the whole answer. There is also a stability problem. Dark matter in the quantities implied by the core concentration would, over billions of years, tend to spread out unless something were actively holding it together. The expanding universe works against concentration. Regions of dark matter that are not locked into a deep gravitational well lose their coherence over time. The core appears to have maintained its concentration across an extraordinary span of cosmic history. That kind of stability requires either an immense amount of mass packed into a relatively small volume, creating a gravitational well deep enough to resist dispersal, or some ongoing physical process that maintains the concentration against the natural tendency to spread. There is a speculative idea that a small number of theorists have raised in connection with anomalies like this one. What if dark matter is not as simple as our standard models assume? What if certain exotic forms of dark matter can interact with themselves in ways we have not yet detected, producing faint energy outputs through self-annihilation or decay? Such interactions could in theory generate a small but persistent warmth. This idea remains unproven. No experiment has confirmed self-interacting dark matter. But the warmth at the core of this structure is exactly the kind of observation that keeps such ideas alive at the edges of physics. What we know for certain is this: the core is not empty. It is not purely dark matter. It is warm, it is stable, and it has been sitting there, quietly generating its signal since long before our planet formed. Something is inside this structure. And the skeleton of the universe itself, the vast web of filaments and voids that gives the cosmos its shape, offers the next clue about what that something might be. The universe is not a random scattering of galaxies thrown across the dark like seeds tossed by a careless hand. It has architecture, it has bones, and once you learn to see them, you cannot unsee them. The largest skeleton in existence stretches across the entire observable cosmos, and astronomers call it the cosmic web. Picture a three-dimensional spider's web spanning billions of light years in every direction. The threads of this web are called filaments, long rope-like rivers of gas, dark matter, and galaxies, all strung together by gravity over billions of years of slow, patient accumulation. Where multiple filaments cross, matter piles up into dense knots. These knots are the galaxy clusters, the great cities of the cosmos, containing thousands of galaxies packed relatively close together, bound by mutual gravity, burning with the combined light of trillions of stars. Between the filaments lie the voids, enormous empty regions where almost nothing exists. No galaxies, no stars, just space, dark and quiet, stretching for hundreds of millions of light years, with barely a whisper of matter to break the silence. This web did not appear overnight. It grew. In the earliest moments after the Big Bang, matter was spread almost evenly throughout the universe. Almost, but not perfectly. Tiny variations in density existed, regions that were fractionally heavier than their neighbors by amounts so small you would need scientific notation to write them down. But gravity does not care about size. It cares about time. And it had plenty of time. Over millions of years, those slightly denser regions pulled in surrounding matter. Over hundreds of millions of years, that matter organized into sheets and walls. Over billions of years, those sheets collapsed into the filaments we map today, and galaxies formed along them like towns forming along a river, drawn to the flow of material and energy that the filaments provided. The longest confirmed filaments stretch hundreds of millions of light years. They are not solid objects. You could not touch one or land on one. They are more like currents in an ocean, visible not because the current itself glows, but because everything caught in it galaxies, gas clouds, dark matter halos follows the same path and lines up in the same direction. Galaxy surveys have mapped these filaments in stunning detail, revealing a universe that looks less like a random explosion and more like a living network, pulsing with structure at every scale. Webb has deepened this picture enormously. Its infrared vision detects not just the galaxies strung along the filaments, but the gas between them. The warm tendrils of material connecting galaxy clusters, the faint bridges of hydrogen and helium that span the gaps between neighboring galaxies like threads of silk connecting the beads of a necklace. Webb has even captured the early seeds of filament formation in the distant universe, showing us the cosmic web as it looked when it was still young and still assembling itself from the raw materials of the Big Bang. Now here is why all of this matters for what Webb found 6 billion light-years away. The structure sits in a region of space where the cosmic web should be well understood. At that distance, we have good maps. We know roughly where the major filaments are, how dense they should be, and how the galaxies along them should be distributed. The structure Webb detected does not fit neatly into this known pattern. Its scale is too large for a standard filament. Filaments are long and thin, rivers of matter flowing between the dense knots of galaxy clusters. They do not have the kind of concentrated mass center that this structure possesses. Its mass distribution is too tight, too focused for the diffuse, spread-out profile of a typical filament. A filament is like a highway connecting two cities. Matter flows along it. Galaxies line up beside it. But no highway has a city of this size and density sitting at its midpoint. No known filament has a concentrated gravitational anchor at its center, generating its own distinct infrared signal and bending light more sharply than the surrounding web can account for. The elongated shape of the structure does resemble a filament in outline. That resemblance is part of what makes the discovery so tantalizing and so frustrating. It looks like it could be a filament. It has the right general geometry. But the internal architecture is wrong. The concentrated core, the defined edges, the ancient galaxies arranged along its axis in a Some researchers have argued that these simulations may be missing rare but real configurations, places where filaments thicken or develop internal structure that standard models do not predict. The structure Webb found could be evidence for exactly this kind of hidden complexity, or it could be something else entirely. Something that the cosmic Webb framework was never designed to describe. There is a speculative idea, discussed mostly in theoretical circles, that the very early universe may have produced what some call protostructures, enormous concentrations of mass that formed before the cosmic web itself had fully taken shape. These protostructures would have been the first large-scale organizations of matter in the universe, predating the filaments and clusters we see today. If such objects existed, they would have been absorbed into the growing web over billions of years, their original identities erased as the web formed around them and through them. But in rare cases, if the initial mass concentration was large enough and dense enough, the protostructure might have survived, not as a separate object floating outside the web, but as something embedded within it. A fossil from an earlier era of cosmic history, still carrying the gravitational fingerprint of conditions that existed before the web was born. The structure Webb found shows signs consistent with this idea. Its age, implied by the ancient galaxies surrounding it, suggests it was in place before the local region of the cosmic web had finished forming. Its mass concentration suggests it was shaped by forces operating at a time when the universe was simpler, denser, and governed by conditions that no longer exist in most regions of space. And its relationship to the surrounding web, sitting within it, but not behaving like a normal part of it, suggests something that was here first, and that the web grew around rather than something the web produced. The cosmic web is the context for everything large in the universe. It is the map on which all other structures are drawn. But this structure breaks out of that map. It refuses to be just another thread or just another knot. It plays by rules that may be older than the web itself, rules that take us back to the mathematical framework that describes how the entire universe is supposed to work, and to the uncomfortable places where that framework begins to crack under the weight of what Webb has shown us. Every field of science has a rulebook, a set of equations and principles that tell you what should happen under given conditions. In cosmology, the study of the universe at its largest scales, that rulebook has a name: Lambda CDM. It stands for Lambda Cold Dark Matter, and it is the standard model of how the cosmos formed, how it evolved, and how it came to look the way it does today. Lambda CDM is not a guess. It is not a rough sketch waiting to be replaced. It is one of the most thoroughly tested frameworks in all of science, confirmed by decades of observations from satellites, ground telescopes, and instruments measuring everything from the faint glow of the early universe to the movements of distant galaxy clusters. The model works extraordinarily well. It predicts the pattern of temperature fluctuations in the cosmic microwave background, the afterglow of the Big Bang, with stunning precision. It explains why galaxies cluster the way they do. It accounts for the observed expansion of the universe and the mysterious acceleration of that expansion driven by dark energy. The lambda in the model's name. It provides a timeline for structure formation that matches what we see when we look at galaxies at different distances and therefore different ages. Lambda CDM is the foundation on which modern cosmology stands. And then, Webb pointed at a patch of sky 6 billion light-years away and found something that makes that foundation tremble. The model predicts specific things about how structures form. It says small structures form first. Dark matter collects into clumps. Those clumps merge into larger halos. Galaxies form inside those halos. Galaxy groups form as galaxies are drawn together by gravity. Groups merge into clusters. Clusters connect through filaments. The whole process is called hierarchical structure formation. Bottom up, small to large, simple to complex. The model also predicts how fast this process can happen. The rate depends on the density of matter, the rate of cosmic expansion, and the strength of gravity. Given these ingredients, Lambda CDM draws a timeline. It tells you how massive a structure can be at any given moment in cosmic history. It tells you how concentrated that mass can be. It tells you how organized the structure can appear. The structure Webb found exceeds these predictions, not by a small margin, not in ways that can be easily absorbed into the existing framework by adjusting a few numbers. The violations are significant enough that they have forced researchers to ask uncomfortable questions about whether something is missing from the model itself. Start with mass concentration. At the distance Webb observed, the standard model allows for large structures. Galaxy clusters exist at this epoch. Superclusters are beginning to form. But the level of central mass concentration seen at the core of this structure is not predicted. Lambda CDM expects structures at this distance to be looser, more spread out, still in the process of assembling. A tightly organized structure with a defined center and a compact gravitational anchor should not have had time to form. The model says it takes longer than the universe had provided by that point. Then, consider the shape. The elongated spindle geometry of the structure raises questions about what forces created it. Standard structure formation tends to produce rounder or more irregular shapes at these scales. Gravity pulls inward from all directions. Over time, things settle towards spherical configurations. A structure with clean, defined elongation suggests either very unusual initial conditions or a formation process that the model does not fully describe. Something shaped this object in a way that ordinary gravitational collapse would not naturally produce. And then there is the warmth. Lambda CDM has no built-in explanation for a stable, concentrated mass generating a persistent infrared excess at the core of a structure this large. The model describes how mass accumulates under gravity. It does not describe what would cause that mass to organize into a warm, compact source sitting at the center of a billion light-year scale formation and remaining stable for billions of years. Scientists are cautious people. They do not declare a model broken based on a single observation, no matter how strange. Lambda CDM has survived many challenges over the decades. Anomalies appear, and then they are explained. Parameters are adjusted, new pieces of physics are added. The framework bends but does not break. That is how science works. Progress happens not by throwing away everything that came before, but by refining and extending it. But this structure arrives in the context of other anomalies Webb has revealed. Since it began observing, Webb has found massive galaxies that formed too early, black holes that grew too fast, galaxy clusters that assembled before the timeline said they should have been possible. Each one individually might be dismissed as a statistical outlier, a rare fluctuation at the tail end of what the model permits. But the anomalies are accumulating. They are beginning to form a pattern. And the pattern says the early universe was more efficient at building structure than Lambda CDM predicts. There is active debate within the scientific community about what this means. Some researchers argue that the model's parameters simply need to be recalibrated. Perhaps the density fluctuations in the early universe were slightly more extreme than current estimates suggest. Perhaps dark matter behaves in ways our simplest models do not capture. Perhaps there are feedback processes in early galaxy formation that we have not yet properly accounted for. These adjustments would stretch Lambda CDM but not replace it. Other researchers argue that the accumulating evidence points towards something more fundamental. Perhaps the physics of the very early universe, the first fractions of a second after the Big Bang, was different in ways we have not yet understood. Perhaps the seeds from which all structure grew were not the smooth, nearly featureless fluctuations that standard inflation predicts, but something more complex, more variable, more extreme in certain rare regions. Perhaps the universe was handed unusual starting conditions in some locations, and the structures growing from those seeds break the rules that govern ordinary regions of space. There is a speculative possibility that sits at the far edge of this debate. What if Lambda CDM is not wrong but incomplete? What if there is a piece of physics operating at the largest scales or at the earliest times that the model simply does not include? Not because anyone made a mistake, but because we have never had the instruments to see its effects until now. Webb is that instrument. It sees further, deeper, and more clearly than anything before it, and what it sees is pushing against the walls of a framework that was built before anyone knew structures like this could exist. Both theories attempting to explain this structure, the megafilament collapse and the active source hypothesis, sit outside the comfort zone of Lambda CDM. Both require the model to stretch in directions it was not designed to go, and understanding those two theories, what they propose, and why neither fully satisfies, is where the next step of our journey leads. When something is found that does not fit the known categories, scientists do not simply throw up their hands and declare mystery. They build explanations. They construct frameworks that might account for the evidence, without abandoning the physics that has served them well. Two such explanations have emerged for the structure Webb found, two competing theories, each with strengths, each with weaknesses, and neither able to fully claim victory over the other. The first theory is elegant. It stays within the boundaries of known physics, asking the universe only to stretch a little, not to break. It proposes that what Webb found is a megafilament, a primordial structure that formed during the earliest phases of cosmic history, when conditions allowed certain overdense regions to collapse faster and more completely than the standard models typically permit. In the standard picture, the primordial filaments that existed in the young universe are gone now. They collapsed, fragmented, and dissolved into the cosmic web. Their original identity as unified structures was erased billions of years ago as galaxies formed along them and clusters grew at their intersections. But in certain rare regions, where initial conditions were unusually dense or where the surrounding expansion of space was slightly slower, a filament might have survived. Not as a gas structure, which would have dispersed long ago, but as a dark matter skeleton, a gravitational remnant holding the outline of its original form across billions of years. The elongated shape of the structure fits this picture remarkably well. Primordial filaments were not spheres. They were stretched along the directions of least resistance in the early density field. Compressed along others, the spindle-like geometry Webb measured, wide across the middle and tapered at the ends, matches what theoretical models predict for a collapsed megafilament viewed from a specific angle. The mass concentration at the center is also consistent with this theory. As a filament collapses inward under its own gravity, material flows toward the midpoint. The center becomes the densest region. If the collapse was complete enough and ancient enough, that central mass could have been sitting there for billions of years, largely stable, while the galaxies that formed around it slowly orbited its gravitational anchor. This theory works. It does not require new physics. It does not demand that we throw away Lambda CDM and start over. It simply asks us to accept that rare, extreme conditions in the early universe could produce rare, extreme outcomes. The megafilament hypothesis is tidy. It is defensible. And it has one significant problem. The warmth. The infrared excess coming from the core does not fit comfortably within this framework. A collapsed dark matter structure, ancient and stable, should be cold. Dark matter does not heat up. It does not radiate. It does not glow. It simply sits there, bending space, doing nothing that would warm the surrounding region. The megafilament theory can explain the shape. It can explain the mass distribution. It struggles to explain why the core is generating a consistent infrared signal that Webb measured across multiple observation windows. This is where the second theory enters. It is not tidy. It does not stay politely within the bounds of known physics. It asks the universe to make room for something new. The rival theory begins with the infrared signal as the central piece of evidence, rather than an awkward detail to be explained away. It proposes that what sits at the center of this structure is not a passive remnant of the early universe. It is an active source, something generating its own gravitational field and its own energy output, not a relic of something that happened long ago, but a process that is still happening now, or at least was still happening 6 billion years ago when Webb observed it. The class of objects most seriously discussed in this context is something called a quasar remnant, but at a scale and configuration that has no confirmed precedent. Quasars are among the most energetic objects in the known universe. They are powered by supermassive black holes actively consuming surrounding material. In their active phase, quasars outshine entire galaxies, blazing with more light than 100 billion stars combined. But quasars do not stay active forever. They burn through their fuel. They quiet down. They leave behind a black hole sitting in the dark, massive but silent, no longer feeding, no longer glowing. Some researchers have proposed that the core of this structure could be the remnant of a quasar-like object of extraordinary scale. Not a typical supermassive black hole at the center of a single galaxy, something operating at a different level entirely. A concentration of mass so great that it has been maintaining a slow, steady energy output for billions of years without exhausting its supply. A dormant giant still warm enough to register on Webb's detectors, even though its active phase ended long ago. The numbers required for this theory are extreme. The mass at the core, if this interpretation is correct, would far exceed anything in the confirmed catalogue of cosmic objects. It would require a formation mechanism that predates the known population of supermassive black holes and operates on a scale our current models do not describe. Critics focus on exactly this point. You cannot simply invent a new class of object to explain an anomaly. Science demands more than a hypothesis that fits. It demands corroboration. Evidence from other observations, signatures at other wavelengths, independent confirmation from other instruments. And here is where the story becomes genuinely uncomfortable for both sides. The corroborating evidence is ambiguous. It neither clearly confirms the active source theory nor cleanly rules it out. Webb's data shows something warm and gravitationally dominant at the core. It does not yet show the specific spectral signature that would definitively identify what type of object is there. The X-ray data is inconclusive. The radio data shows hints of past energetic activity, but no clear smoking gun. Both theories remain standing. Both are being tested, and the people doing the testing are careful not to commit prematurely. The history of astronomy offers sobering lessons here. Some anomalies that seemed to demand new physics turned out to be ordinary objects viewed from unusual angles or instrument artifacts nobody initially suspected. Other anomalies, initially dismissed as likely errors, turned out to be genuine discoveries that changed everything. The planet Neptune was found because of a small gravitational anomaly. Pulsars were initially labeled as possible signals from extraterrestrial intelligence before their true nature as spinning neutron stars was understood. Dark matter itself was first proposed to explain a gravitational anomaly in galaxy rotation that seemed impossible under ordinary physics. This structure sits in the same uncertain territory. Neither theory has won. Neither has been defeated. The data keeps accumulating. And somewhere in the gap between what we expected and what we found, the truth is waiting to be identified. The most dramatic possibility, the one that neither theory fully embraces but that both point toward in different ways, involves objects so extreme and so ancient that their existence would require us to rethink not just structure formation, but the very first moments of the cosmos itself. Before galaxies existed, before the first stars ignited, before the cosmic web had stretched its filaments across the void, the universe was a different place. Not empty exactly, not silent, but formless in the way that matters most. There were no structures yet, just an ocean of gas and dark matter spreading in every direction, almost perfectly smooth, with tiny ripples of density running through it like waves across a pond after a pebble has been dropped. Those ripples are called primordial density fluctuations. They were seeded in the first fraction of a second after the Big Bang, imprinted into the fabric of space by quantum processes operating at scales almost impossibly small. And they are the seeds of everything that came after. Every galaxy, every star, every planet, every atom in your body traces its origin back to those ancient ripples, those tiny variations in density that gravity would spend billions of years amplifying into the structures we see today. In most regions of the universe, Those ripples grew at a predictable pace. Slightly denser regions pulled in surrounding material. Over tens of millions of years, sheets of gas and dark matter began to form. Those sheets collapsed into filaments. Galaxies formed along the filaments. Clusters formed where filaments crossed. The hierarchy unfolded from small to large, bottom to top, exactly as Lambda CDM predicts. But what if in certain rare regions the conditions were different? What if the initial density fluctuations were not just slightly stronger, but dramatically stronger, strong enough to collapse directly into massive compact objects without waiting for the slow assembly process that built everything else? This is the idea behind primordial black holes. The concept is not new. Theoretical physicists proposed it decades ago in the extreme conditions of the very early universe. Fractions of a second after the Big Bang, regions of unusually high density could have collapsed under their own gravity before the normal expansion of space had time to dilute them. These collapses would have formed black holes directly from the raw material of the early cosmos. Not from dying stars, which did not yet exist, not from colliding galaxies, which would not form for hundreds of millions of years. Just pure gravitational collapse of primordial matter into singularities wrapped in event horizons. Ordinary black holes, the ones we detect through gravitational waves and X-ray emissions, form when massive stars exhaust their fuel and collapse. They typically range from a few times the mass of our Sun to perhaps 100 times. Supermassive black holes, the giants sitting at the centers of galaxies, can reach billions of solar masses. But they are thought to have grown gradually over cosmic time, feeding on surrounding gas and merging with other black holes across billions of years. Primordial black holes skipped all of that. They formed in an instant, at the very beginning, from conditions that no longer exist anywhere in the universe. And here is the critical point. There is no upper limit in principle to how massive they could be. If the density fluctuation that seeded them was large enough, the resulting black hole could be enormous, far larger than anything stellar evolution could produce, far older than anything that formed through ordinary processes. The primordial black hole cluster hypothesis proposes that what sits at the core of the structure Webb found is not a single object. It is a collection of them. Potentially thousands of ancient black holes formed in the first moments of the universe, orbiting a shared gravitational center in a configuration that has remained stable for nearly the entire history of cosmic time. This would explain several features of the data that other theories struggle with. A distributed mass source rather than a single point would produce the broad gravitational footprint Webb measured. The combined mass of thousands of ancient black holes could account for the extreme lensing and the anomalous redshift of background light passing through the core, and crucially, a black hole cluster would generate heat through a process called dynamical friction. Dynamical friction is what happens when massive objects move through a field of other massive objects. They lose energy through gravitational interactions. That lost energy has to go somewhere. It heats the surrounding material. It produces radiation. A dense cluster of black holes, slowly churning against each other over billions of years, would generate exactly the kind of faint, persistent infrared warmth that Webb detected at the core. Not a blazing output. Not a quasar-level beacon, just a slow, steady warmth produced by the gravitational grinding of ancient compact objects against each other, and against any gas or dust that wanders too close. The numbers required are extreme. The total mass implied by the gravitational data, if distributed across a cluster of primordial black holes, would require formation conditions beyond the upper range of what standard inflationary models predict. But not impossibly beyond, not in the realm of fantasy. The primordial black hole cluster hypothesis sits at the frontier of what is theoretically imaginable. It has not been confirmed. It has not been ruled out. But it creates a problem that reaches far beyond this single structure, a timeline problem. If the core of this structure is what this hypothesis suggests, then it formed in the first moments after the Big Bang. It was already in place, already massive, already gravitationally dominant, when the universe was less than a second old. The ancient galaxies surrounding the structure, which appear to have had their star formation suppressed by the core's gravitational influence, were affected by something that existed before them, something that was already old when they were born. This challenges the most basic assumptions about sequence and causation in cosmic history. Structures are supposed to build up over time. Small things come first, big things come later. But a primordial black hole cluster would have been big from the very beginning. It would not have built itself through accumulation. It would have been handed its mass by the conditions of the Big Bang itself. There is a speculative extension of this idea that some theorists discuss quietly, usually with many qualifiers and disclaimers. What if the density fluctuations that seeded primordial black holes were not random? What if they were imprinted by processes that occurred before the Big Bang in whatever state of existence preceded our universe? This pushes into territory that physics cannot currently test. We have no way to observe what came before the Big Bang. We may never have such a way, but the existence of structures like this one, structures that seem too big, too old, too organized to fit our models, keeps such questions alive at the very edge of scientific thought. Whether the core of this structure is a primordial black hole cluster remains unproven. But the hypothesis draws a direct line from what Webb observed to the deepest questions about cosmic origins, and the search for answers has drawn every major observatory toward this patch of sky, each one adding its own piece to a puzzle that grows more complex with every new observation. When something strange enough is found in the sky, the entire network of human observatories turns to look. James Webb does not work alone. It is the crown jewel of a global system of telescopes, each one sensitive to different wavelengths, each capable of adding a different layer of information to any discovery. Radio telescopes hear frequencies invisible to optical instruments. X-ray observatories catch high-energy radiation that passes through ordinary detectors without leaving a trace. Ground-based spectrographs break light into its component colors and read the chemical fingerprints hidden inside. Together, these instruments form a single vast eye, far more powerful than any one piece could be on its own. The structure Webb found triggered exactly this kind of coordinated response. Within months of the initial discovery, observation requests had been submitted to nearly every major facility capable of contributing useful data. One by one, they turned their attention to that distant patch of sky and began gathering evidence from wavelengths Webb itself cannot see. The Atacama Large Millimeter Array came first. ALMA sits high in the Chilean desert, a collection of dozens of radio dishes spread across a plateau so dry and so elevated that the air above it is nearly transparent to millimeter wave radiation. ALMA sees cold gas and dust, the raw materials from which stars are born, and the remnants left behind when energetic events disturb the space between galaxies. When ALMA looked at the region surrounding the structure, it found something interesting. The gas near the core showed signs of disturbance, not fresh disturbance, old disturbance. Patterns in the gas distribution that suggested powerful outflows had swept through the region long ago, pushing material aside, heating it, leaving a structural imprint that persists even though the source of those outflows has long since quieted. This is consistent with something energetic having been active at the core in the distant past. A quasar, a massive black hole feeding on surrounding material and blasting jets of radiation and particles into the surrounding space. The evidence ALMA captured was not the activity itself, but the scar it left behind. A fossil record written in the arrangement of gas molecules across millions of light years. Next came the X-ray observatories. The Chandra X-ray Observatory, orbiting above Earth's atmosphere where X-rays can reach its detectors without being absorbed, examined the core region for signatures of hot gas. When matter falls toward a massive compact object, it heats up. It reaches temperatures of millions of degrees. At those temperatures, it glows in X-rays. If something at the core was actively consuming material right now, or had been doing so in the recent past, Chandra should see the glow. What Chandra found was subtle. There was no bright X-ray source at the core, no obvious beacon announcing a feeding black hole. But there was a diffuse X-ray excess spread across the region. More X-ray emission than the known galaxy population could account for. Not enough to confirm an active source. Not little enough to rule one out. The X-ray data sat in an uncomfortable middle ground, consistent with either a dormant remnant still faintly warm or a collection of smaller sources blending together into a soft glow that no single object could claim. The European Space Agency's XME Newton satellite provided complementary data. Its detectors operate at slightly different sensitivities than Chandra's, capturing a broader range of X-ray energies. The results matched. A faint excess. No clear point source. The same ambiguous signature that refused to commit to either explanation. On the ground, the Very Large Telescope in Chile turned its spectrographs toward the structure. Spectroscopy is where astronomy becomes chemistry. By spreading light into its component wavelengths, spectrographs reveal what something is made of, how fast it is moving, and what physical processes are operating inside it. The VILT focused on the faint emission line Webb had detected during its second observation run. That line, sitting at a specific wavelength, had matched nothing in existing catalogues. It was not a known signature of hot gas. It was not a standard marker of any identified astronomical object. It simply sat there, unexplained, demanding attention. The VELT data refined the measurement. The wavelength was pinned down more precisely. Researchers searched databases of atomic and molecular transitions looking for a match. They compared it against every known emission process that could operate in deep space. As of now, no definitive identification has been made. The spectral line remains unexplained. It sits in the data like a word in a language nobody has yet learned to read. There is a history in astronomy of unidentified spectral lines eventually being explained. Sometimes the solution comes quickly. Sometimes it takes decades. Helium, now known as the second most common element in the universe, was first discovered as an unexplained spectral line in sunlight. For years it was called an unknown element before laboratory experiments on Earth finally produced the same signature and revealed its identity. The line Webb found at the core of this structure could follow a similar path. Or it could remain mysterious for far longer. The combined picture from all these observations is this. Something powerful was active at the core of this structure in the distant past. It drove outflows that disturbed the surrounding gas. It may have generated X-rays at a level that has since faded to a faint diffuse glow. It left behind a chemical or physical signature in the form of an emission line that no one has yet identified, and it continues to produce a faint infrared warmth that Webb can detect even now, 6 billion years after the light carrying that warmth began its journey toward us. The most straightforward interpretation is that the core was once home to something like an extraordinarily massive quasar, now dormant. Its feeding phase ended long ago. Its jets have faded, but its mass remains, still anchoring the structure, still bending light, still warm enough to whisper its presence across billions of light years. There is a speculative alternative that some researchers have raised. What if the unidentified spectral line is not a chemical signature at all, but a physical one? What if it represents some process we have not yet catalogued, something that happens only under conditions so extreme that no laboratory on Earth could replicate them? The cores of massive compact objects produce environments unlike anything else in the universe. Densities beyond imagination. Gravitational fields that twist space into knots. Perhaps in those conditions, physics does things we have not yet learned to recognize. This remains speculation. No evidence confirms it. But the spectral line remains unexplained, and until it is explained, every possibility stays on the table. The telescopes will keep watching. More data will arrive. And somewhere in that stream of numbers, the answer is waiting to be decoded. What that answer means for our understanding of the universe, and for the limits of what we can ever hope to know, is the final destination of this journey. There is a boundary at the edge of what we can know. It is not a wall you could touch. It is not a place you could visit. It is a limit built into the nature of light itself and the nature of time. Light travels at a fixed speed. The universe has been expanding since the Big Bang. Beyond a certain distance, the light emitted by any object has not had enough time to reach us. That region is disconnected from us. We cannot see it. We cannot signal it. We cannot receive any information from it. It is as unreachable as yesterday. Even within the observable universe, there are softer limits. Objects that existed very early in cosmic history have had their light stretched by billions of years of expansion. Wavelengths that began as visible light have redshifted into infrared. Wavelengths that began as infrared have stretched into radio waves. Some of that ancient light has grown so faint and so distorted that no instrument we could ever build would be able to read it clearly. Webb pushes these limits further than anything before it, but it does not dissolve them. The core of this structure sits 6 billion light years away. We observe it as it was 6 billion years ago. To understand how it formed, we would need to see it as it was 10 billion years ago, 12 billion years ago, when whatever process assembled it was still underway. We cannot do that directly. The light from those earlier epochs either has not yet reached us, has already passed us long ago, or has been diluted beyond detection. This is a fundamental limit, not a technological one, a physical one. Certain questions about this structure may remain permanently unanswered. We can measure what it looked like 6 billion years ago with extraordinary precision. We can build models of what it might have looked like earlier. We can compare it to other structures and use those comparisons to constrain our theories. But we cannot watch it being born. The universe does not offer replays, and the nature of what sits at the core presents its own barrier. Black holes, if that is what is there, are information destroyers from the outside observer's perspective. Whatever history they carry, whatever conditions they formed under, is sealed behind an event horizon. Light cannot escape from inside a black hole. Neither can any signal of any kind. The interior state of a black hole is as inaccessible to us as the moment before the Big Bang. This matters not just for this structure, but for the broader questions it raises. If the early universe produced objects of this kind, and if those objects carry in their properties the fingerprints of conditions that existed in the first fractions of a second after everything began, we may never be able to read those fingerprints directly. The evidence is locked away behind horizons we cannot cross. What we can do is measure effects. We can count the gravitational waves produced when massive objects merge. We can map the large-scale structure of the universe and compare it to models with different assumptions about early conditions. We can build better telescopes and look at more objects and accumulate statistics that inch our understanding forward. Progress does not stop just because some answers lie beyond reach. It simply becomes more patient. There is a question that has lingered at the edge of astronomy for more than 70 years. If the universe is so large, so old, and so full of stars, where is everyone? The Fermi paradox is the name given to the apparent contradiction between the high probability that intelligent life exists elsewhere and the complete absence of any confirmed evidence that it does. Decades of listening have produced no signal. The sky, when examined carefully, sounds empty of anything made by minds. Many explanations have been proposed. Perhaps intelligent life is extraordinarily rare. Perhaps civilizations destroy themselves before they can reach out across the stars. Perhaps the distances are simply too great and signals too faint. Perhaps communication happens in ways we have not learned to recognize. What this structure adds to that conversation is subtle but worth sitting with. If the early universe could produce something like this, a massive, organized, ancient structure with a concentrated core and a gravitational influence stretching across millions of light years, then our picture of what the cosmos is capable of building may be incomplete. And an incomplete picture of physical possibilities is also an incomplete picture of what environments might have allowed life to emerge, persist, and develop over timescales longer than we typically imagine. This is speculative. The connection between a gravitational anomaly and the question of life elsewhere is indirect. But the Fermi paradox ultimately rests on assumptions about how the universe works. Every discovery that challenges those assumptions adds a new variable to the equation. The silence of the sky remains. No signal has arrived. But the silence is heard against an increasingly unfamiliar backdrop. A universe stranger than we thought may hold possibilities we have not yet imagined. Future telescopes will continue this work. The extremely large telescope, currently under construction in Chile, will have a mirror nearly 40 meters across. It will be capable of spectroscopic observations beyond anything Webb can achieve. The Nancy Grace Roman Space Telescope will survey wide fields of deep space, potentially finding similar structures elsewhere that could be compared to this one. Each new instrument adds another piece to the puzzle. Something sits out there in the dark, 6 billion light years away. Massive, old, warm, organized, bending light, shaping galaxies, generating a signal no catalogue explains, and James Webb, floating cold and patient a million miles from Earth, keeps watching. Whatever is at the core has been waiting billions of years to be understood. We have only just begun to ask the right questions. And now, as this journey draws to a close, let your breath slow. Let your thoughts settle like dust falling through still air. The universe is vast beyond comprehension, ancient beyond memory, and stranger than any story we have told about it. But you are part of it. Your atoms were forged in the hearts of stars that died before Earth was born. The same forces that shaped that distant structure also shaped the ground beneath you, the air in your lungs, the quiet rhythm of your resting heart. You do not need to hold all of this in your mind tonight. It will still be there tomorrow. The structure will still be bending light. Webb will still be watching. And you here, now, can simply rest. Let the immensity become a blanket rather than a burden. Let the mystery become a lullaby rather than a question demanding answers. The cosmos has time. So do you. Close your eyes. Let the darkness behind your eyelids be the same darkness that stretches between galaxies, soft and patient, and full of things not yet discovered. You are safe here. You are home, and somewhere, 6 billion light years away, something ancient waits quietly, as it has for longer than worlds have existed, for the next question we will learn to ask.